All right, let's learn about the difference in algorithm efficiency. So these two will print an even number between 2 and 100, and they will do a little bit different from each other. So version number one will try to check if each number remainder is divided by 2, remainder is equivalent to 0, and it will print. So it will be big O of n. For version number 2, it will just increment the number by 2, and it will print right away. So version number 1 is a little bit slower than version number 2. Version number 2 will be faster because it just jump right into the even number, right? So in this case, version number 2 will be big O of n divided by 2, but as the data grow larger, it will end up with big O of n, because the constant number right here become insignificant. The reason why we say that is basically uh, it becomes slower and slower, and it end up with uh, linear linear type of big O, worst case scenario, right? And which is why we have to completely change the how we do things, and the constant number shouldn't be the one that we count in how we uh, make our algorithm efficient. So this constant number make things a little bit different, but it's not that significant when it comes to uh, optimizing our algorithm. So we have to completely change the way big O is. So in this case, in binary search or binary sort, that they have this big O of n log n or log n. And in this case, between big O of 1 and n will be log n, right? Which is binary search, I think. Yeah. And n square, something like that. Between them, the big O have to be completely different. And the constant doesn't have to be included, right? So that's why we have to watch out for this. And this example is coming from a Common Sense Guide Data Structure and Algorithm, and it's a really good book. So I noticed that this is a really good comparison between because of and from version different two algorithms with a different type of learning. Okay, uh, that's our lesson for today.